Hi, this video is to introduce some really important concepts, the calibration curves and external standards, blanks, and then a variety of terms related to method verification and method validation. First, we'll discuss calibration curves. Most of the time when somebody's discussing a calibration curve, what they're really talking about is the method of external standards. Now, unless you go further to study internal standards and standard additions, external standards might seem like unnecessary explanation, and so a lot of people do just generally call this a calibration curve. So what is being calibrated? It's a really wonderful thing to think about. What's being calibrated is that for each analyte, which we will term A, we calibrate the proportion between the concentration of the analyte and the signal, and the proportionality constant is Ka. So in essence, what we're going to say is that the signal for an analyte is going to be equal to some proportionality constant for that analyte times the concentration of the analyte. So really what's calibrated is Ka. We want to know what is the response for our sample under these conditions using this instrument. Now you notice that single point standardization, meaning just doing this one thing right here of saying, hey, look, I got a sample that was 115 parts per million, and I know that, and I get an absorbance of 0.4. And this allows me to get some proportionality constant here. And then I can use that forevermore, right? So we can do that. We can like turn our computer on and say, okay, well, 0.4 divided by, it's dark in here, the 115. Okay, well, this has to be a Ka equal to 0.00347. Yeah, okay, sig figs. I might as well put a couple more zeros over there so my sig figs match. And what is that? Well, it's inverse ppm because absorbance is arbitrary units, and we already have ppm on the right-hand side. So why is it less desirable to do this single point standardization than to do a multiple point standardization where you would use multiple samples? Well, the first thing is that if you're doing it like this, you're going to have any error made in this one measurement carry over into the calculation of all of your concentrations. So if you mess this up at all, it's propagated forward through everything else that you do. The other thing is that if you're only basing the Ka on one concentration, you're really assuming that this linear proportion is there for all of your concentrations, and maybe it's not. What if the concentration is not linear to signal? So you better test more concentrations to figure it out, and testing more concentrations is called multiple point standardization. But if you don't have that situation, if you really have a small concentration range, it can be okay to do a single point calibration. So multiple point calibration is what you might be used to seeing for the calibration curve, and that is what's shown on the right. And this is like a really nice calibration curve. You've got a concentration on the x-axis, you've got beautiful absorbance, and it's pretty linear. And so that's nice. So terminology-wise, sometimes people will confuse sensitivity and selectivity. Sensitivity is essentially the slope of the calibration curve because it's saying how much do you get a change in signal, right? How much does signal go up for any given change in analyte concentration? Well, that's rise over run. That is the slope of the calibration curve. You can think of this anecdotally as a friend of yours might be really sensitive to something. You know, maybe there's something that offends them, but they get offended a lot. So the stimulus, the x-axis, is thing that offends, and response is how offended they are, right? So they're very sensitive about that thing, meaning they have a really large slope of their calibration curve. Now, alternatively, there's selectivity, which is sometimes called specificity. And this is the ability to select a particular species, the analyte, out from all the other species in the sample. What that means is avoiding interferences, that there won't be other things present that will cause you to get a response or a signal. Linearity. The question here is how well does the calibration curve follow a straight line? You should make your calibration curve covering a range of concentrations. You want it to be, if your desired sample concentration is here, at least half or so the intensity up to 1.5 times the intensity. Your sample should be right in the middle of your calibration curve. So you do that, you plot your curve, and then you're going to measure linearity. Really nice one is the square of the correlation coefficient. So this is your R squared. Close to 1 is good. 0.995 is like, yeah, sweet. Really, honestly, less than that, like a 0.95 is actually pretty bad. I've seen some terrible calibration curves that have a 0.95. So a lot of people will think of the R squared and they'll end there. They'll say, hey, my calibration curve has a great R squared, we're done. You should probably look further. First of all, the y-intercept. So you have y equals mx plus b, right? There's your good old calibration curve equation for linear. So y equals mx plus b. What we're concerned about right now is the plus b, right? This is your intercept. Ideally, it's 0. If it's large, if it's, like greater than 10% of the high end of your calibration curve, then you've probably got a problem. Really, what this intercept is doing is testing how good your blink subtraction is. And we'll talk about blinks a little bit later. So should be 0. The other thing is to keep your eyes open when you're making a calibration curve. A lot of times you'll see a curve like this, where it's rising and then it's going to level off. So don't just blindly fit a line to the whole curve. This red line that I've drawn on top of it is what just Microsoft Excel will tell you is the linear trend line for all of this data, but clearly it doesn't fit well. So you need to only fit a line to the linear dynamic range, or the green area there. And so just be careful if you want to, if you need to, as long as the response continues to increase. So you do get an increase from here up to there. Let's see, sorry, it's not really level. So that part is still dynamic, it's just not linear dynamic. So if you have to use it, make sure you're not doing a linear fit. Which leads us to range. Range is just plain old range, the concentration interval over which your specifications are met. And that means for linearity, accuracy, and precision. It really means the usable range. Your data is good in that area. Don't confuse it with linear range, right? Which means the calibration curve is linear. Why is this something you could confuse it with? Well, maybe your accuracy and precision is not good during that entire linear range. And of course, as demonstrated on the previous slide, dynamic range, you can still have a measurable increase without it being linear. Now, matrix effects are the bane of an analytical chemist's existence, and they're very, very common. So what's shown here is an overlay of 2 different calibration curves. The analyte is perchlorate, and the black line is made with reagent water. Basically, it's distilled water. You get a nice high sensitivity, okay, high slope of this calibration curve. And then the slope is 15 times less when you go and you measure the perchlorate in groundwater. The reason for this is that there are other anions in the solution of the groundwater, and those cause problems, essentially. So what's a matrix? Matrix is everything in your sample other than the analyte. It's the surrounding material of the sample. So matrix effects are when the analyte's response, slope, changes because of the fact that it's in this different matrix. This happens all the time with people. People could be considered to be analytes. People, when they're hanging out with their friends, might be noisy and boisterous. When they're sitting in a class lecture, might be quiet and calm. Their matrix, their surroundings, influences their behavior. Now, of course, molecules aren't people, but whatever, similar idea. This example right here is groundwater. That's an environmental sample. Healthcare samples are also usually very complex. Think about blood and all of the components thereof, and you're going to be pretty likely to encounter matrix effects. One thing that we can try to do is to matrix match. That means to make your standards in a solution that has the same composition as your analytes. And in future videos, you can learn about using spike recovery to test for matrix effects, see if you actually have them. And also you can learn about standard additions, which is a method to correct for matrix effects. But hold on to your ambitiousness to learn those topics until after you've learned the rest of this. Okay, I mentioned a little while ago that the intercept of your calibration curve depends on the blink. So let's spend a moment or two really discussing what I mean by a blank. Blanks are used in order to account for multiple things. One thing is that maybe there are other components in your sample that are interfering, contributing some signal. Maybe some of your analyte is there in something else that you've used. So maybe you've preserved your sample, maybe you've prepared your sample, diluted it with acid, and maybe just a little bit of your analyte is already present in those liquids. You want to subtract that out. You also have the possibility of carryover. Your analyte might have stuck to the equipment surfaces, and so you can test that by a blank. And when you get into titrations in the future, you will need to evaluate the differences between equivalence points and endpoints, where your titration might take a little bit more liquid past the chemical endpoint. So types of blanks. Method blanks have no analyte in them. They go through every single step of the procedure. And that means sample processing, treatment, acidification, whatever it might be. And you're going to subtract this sample blank reading from all other readings before you do your calibration curve and calculate concentrations. Reagent blanks have no analyte. All of the blanks will have no analyte. But the thing about reagent blanks is they've not gone through all of the method steps. They haven't gone through the procedure. Sometimes you can make both method and create reagent blanks and see if your procedure might have introduced some sort of contamination because it might be there in the method blank but not in the reagent blank. Field blanks are similar to method blanks. They've gone through the entire procedure, but they've also been exposed to the site of sampling. So you take this blank, it's a reagent blank to start, you take it to the site where you're sampling, you open the bottle, you close the bottle, you bring it back, and then you put it through the whole procedure. And that's really testing to see if there's something at the sampling site that has contaminated your material. Trip blanks are similar to field blanks. They also go to the sample site, but they're not opened. And so really lets you think about contamination to the transport level. So you can see by comparison of these what aspect it is that you're investigating with each blank. Now, the rest of this is terminology, and I'm sorry terminology is a boring thing without animations and pictures, but it's important. We're really testing to see if the method that we're using is true, and you have to have a language with which to describe that. So, limit of detection and quantitation. Big, busy slide, but similar things. Detection limit. Yeah, I'm whispering right now, and maybe you heard me, maybe you didn't. Maybe the sound of my voice was below the detection limit. So detection limit is the smallest quantity of analyte that is significantly different from the blank. And that's defined as the signal being greater than 3 times the noise. And so your minimum detectable concentration, your detection limit, is 3 times the standard deviation. So notice down here, S is the standard deviation of a low concentration sample, and M is the slope of your calibration curve. So remember, Y equals mx plus b. So you've got M being your slope of your calibration curve. Lower limit of quantitation. Well, okay, if you can just detect it, well, can you really know that you've got it quantified accurately? The lower limit of quantitation is your concentration where the signal is 10 times greater than the noise. And you can trust that you can get that with reasonable accuracy. So it's defined as 10 times this standard deviation divided by the slope of the calibration curve. So why these numbers? Why the 3S? If you think about Gaussian distributions, so this is your normal bell curve, and you've got a Gaussian distribution centered around the blank reading and the sample reading, Y being whatever it is that you're reading for this thing. And you overlay them, you have to think about, well, gosh, if I'm going to say that a signal greater than the sample, so everything this way, signal greater than the sample, is really different from the blank, I better not be wrong. And so there's this little overlapping zone right there. If you have the average values, right, so this is your average blank right here, and you have your average sample value, if those are 3 standard deviations away from each other, then only 1% of the area of a blank lies to the right of the detection limit. And so that means that if you say that your sample has a concentration greater than the detection limit being right here, detection limit is blank plus 3S, okay, then you're only wrong 1% of the time. And if you picture then having your Gaussian distribution for your sample moved away by 10s, just sketching this out, it's not really to scale, you're going to have a minusculely small amount of the signal from the blank continuing out there because your signal from the blank is like flatlined already there. So it's going to continue to be flatlined. So mentioned earlier, sensitivity is the slope of the calibration curve. Specificity is the ability to distinguish analyte from other things or interferences. If you're going to validate your method, you need to make sure that you don't have potential interfering compounds acting like your analyte. So a lot of times you have to add these things. Imagine you're making a pill, a drug. They're going to be byproducts of the reaction. There might be an intermediate from making the compound. Maybe there's a degradation product because as it ages, it decays. Or there's excipients, sugar, salts, things like that that might be put into the pill to help it make a nice, good solid. So you'd want to do an analysis and see, okay, if my drug, in this case it's peak 4, cefotaxime, there, can I spike it with all of these other impurities and still tell them apart, right? It's important to still tell them apart. So one of the great questions I have is new methods and standard methods. So analytical chemists love to make new methods, improve things. When they say that the new method should be compared with a standard method, assuming you have a standard method, is that testing accuracy or precision? What do you think? Well, it's testing accuracy. It's testing nearness to the truth. There are certified reference materials of various types available from NIST, which is your National Institute of Standards and Technology. And you need to make sure that you're getting one of these that's in the same matrix as your sample. That way you can avoid matrix effects and have it be matrix matched. If you analyze this certified reference material, you should get the correct value, the certified value, within the precision of your instrument. Maybe you don't have such a thing, okay? There's no reference material for your particular sample. Then what you can do is compare the results from 2 or more different analytical methods. So use your method, use a separate, different method. If they agree with each other within their precision or plus or minus, then that's probably the true value. You can also take a blank sample and spike it with a known analyte concentration. As long as your blank has the same matrix as your real samples, then you can do this. And you should do your spikes over 3 different concentration ranges to make sure that you're able to create a sample of known concentration over a good range. If it's not possible to make a blank that has your real matrix, because that can sometimes be really hard to make fake blood or fake river water, then you can do the method of standard additions, and that is covered in a separate PowerPoint. So spiking is pretty much your most common way of ensuring accuracy. It helps you determine if you have matrix effects, and honestly, certified reference materials are difficult to come by and expensive, might not always have one. And you really have to think about how accurate do you need to be. Your specifications might be 100 plus or minus 2% is got to be recovered from the spike. Maybe you can have a 5% or 10% range. It depends on how close you need to be. So precision is how well the replicate measurements agree with each other. And here I want to get into the different types of precisions. There's an instrument precision, which is injection precision. It's same sample repeatedly done many times on the same instrument, and it's really testing variation in instrument response. This is usually very low. Intra-assay precision is if you're using aliquots during the course of a day by the same person on the same instruments. So morning versus evening, is it changing or drifting? There's an intermediate precision or ruggedness, which is different people, you versus me, using different instruments on different days in the same lab, okay? And then finally, interlaboratory precision, which is probably your most rigorous precision, is same sample, different people, different labs, different instruments, different days, and those are called round-robin studies, which I like because my name is Robin. Okay, precision can also be analyzed by the coefficient of variation. You might recognize this as percent relative standard deviation because it is standard deviation divided by the mean times 100%. There's something called the Horwitz trumpet, which is shown on the right here. And it's saying that if you have a particular concentration, okay, and you're looking at a fixed precision level, that because your standard deviation here is going to be the same, and this is going to decrease, now you're dividing by a smaller thing as you move from left to right, okay? Getting down to parts per billion there. And so now you're going to get this huge expansion in relative standard deviation, meaning a small error makes a bigger difference when your sample concentration is small. Now, calibration checks. Suppose you're analyzing a ton of samples. Maybe you've got 30 of them. You made your calibration at the start of the day. Is it still valid at the end of the day or throughout? Do you know if your instrument's working properly? Maybe the values have started drifting. So we have what's called a calibration check. It's a sample that you know the concentration of, and you test it just like it was an unknown. And maybe you have to do it every 4 samples, maybe every 10. Kind of depends on how long your sample analysis is and how likely it is to drift. You should get the right answer for this. Performance test samples are a little bit different. So the calibration check, you know the concentration. Performance test samples, somebody knows the calibration, but it's not the analyst. So it's often called a blind sample. This is used to eliminate the bias that the analyst might have. If they know the concentration, they might unconsciously make some movements to get the right answer. And then the manager or somebody else like that will compare what the analyst gets to what they know it to be. So single operator characteristics, how good are you, right, as a person? What's your precision if you do many replicate portions, preferably more than 10 of them? How accurate are you if we can do a t-test, go watch the stats videos, versus the known concentration? What's your detection limit? How clean are you? Let's go check out that reagent blank. You want to look at precision and accuracy for a variety of concentrations, including a low concentration, something near the detection limit. Also, if you have different sample matrices, then you should really look at these things with each sample matrix. Now, ruggedness. Details of ruggedness testing. Well, how do you do it? Broad strokes here. You want to see how each parameter changes the different results. You're going to test the samples in different labs. This is a round-robin study. Difference between robustness and ruggedness. A sample is, or method is going to be rugged if you can change a parameter a little bit and it doesn't affect the results. Some people will call this robustness, but robustness actually means being free of interferences. So ruggedness, make a small change in a parameter, see if the results are acceptable. Things like pH, buffer concentration, temperature, volume, wavelength, all of that. If it's going to be a small change, makes a big difference, it's not rugged. It's sensitive. Sampling. I have a whole other video on sampling. Please check it out. But if your sample sucks, so does the rest of your analysis. End of story. You have to have a good sample before you go on. The samples have to be representative. And just grabbing a good sample doesn't mean it stays a good sample. You might also have to preserve the sample. Preservation might be things like acidifying things to make the metals stay in place, taking a full container, using the right container, glass versus plastic for different samples, refrigerating it, freezing it, not refrigerating it, not freezing it. You need to look into the details for your particular sample. If you do all of that, then you can go forward with your analysis. If you have a bad sample or a degraded sample, everything else is meaningless. And realize that sometimes you can't store it. Sometimes you have to analyze your sample right away. False negatives and false positives. This is seen a lot in the healthcare and also in environmental health. So imagine that you're wanting to say that lead in drinking water is safe. Think of Flint, Michigan. So you are saying, I certify this lead level is below the legal limit. It's safe. Well, a false positive is if I say the sample exceeds the limit, not safe, high, when it's actually low. For example, a pregnancy test says you're pregnant, but you're not. Hey, that happens to guys sometimes. Like if you gave a guy a pregnancy test because you wanted to test this. Anyway, a false negative is if you say the sample is below negative, but it's actually above. So you're not pregnant according to the test, but you actually are. Different situations mean different ones of these are worse. We want to have very few false positives, few false negatives, but sometimes one is worse than the other. It would be worse to say that contaminated water is safe than it is to say that safe water is contaminated, because then you would follow up and continue. Standard operating procedures. Most methods, once they're developed, have specific steps on how to take them through and carry them out. If you're supposed to be using a standard operating procedure, follow it exactly. People put a lot of time and thought into these, and they're designed to prevent you from cutting corners and therefore introducing mistakes. There's also chain of custody. This means that you have to know what's happened to your sample, and particularly for forensic samples and environmental samples, there's a written chain of custody where every person who has handled and stored a sample signs it and goes right from the site of where it was collected to the point that it was analyzed and completely disposed of. And then there's control charts. So you have to assess whether your quality assurance is actually going well. Compare the results to the specifications. So what's going to go on here is that you're going to plot out as a progression of time the average sample, and then you're going to have warning and action lines, and maybe they're based on relative standard deviations, maybe they're based on something else, but anything that is outside of the action line, let's just suppose that you had a sample up here, you would need to stop your process and figure out what's going on. If you've got 2 out of 3 different measurements between the warning and action lines, so kind of up in that zone there, that's a problem. If things are systematically drifting, all above or below, all increasing or decreasing, alternating many, many times, or anything else that's not random, then you've got a problem and need to stop. All right, so there's your 27-minute introduction to calibration curves, blinks, and calibration terminology. I hope you enjoyed, and I hope you learned a lot. Thanks.